Buenos días, bonjour à tous. Good morning, everybody. First of all, I have two presentations this morning. First presentation about my laboratory and another one on my research activities. So I'm going to try to have half an hour for each, like that it won't be too long. If it's too long, Ruben tell me, like that I can shorten a little bit the second presentation. First of all, I would like to thank Armando and Ruben to invite me for this presentation here. It is my first day in Mexico, so I really enjoy, despite the weather, but it's very kind of you to invite me here. So I will present some the research activity of the Laboratoire d'Ingénierie des Matériaux de Bretagne, that we can translate in Laboratory of Engineering of Material or Design of Material, it's the same. I am the director of this lab, and Jean-François is one of the team researcher in this lab. You can have a very nice picture of Lorient, where the lab is located, on a very beautiful sunny day, so it's not so often. So you have to be there when the weather is like that. So it was already said before, but Lorient is located on the west part of France, around 500 kilometers from Paris, and 10,000 kilometers from here, I guess. And the region is known for two things. The first one is these two guys that defend the region against the Roman invader. So they are called Asterix and Obelix. And the second one is the crepe. So it's a kind of Britain tortilla, but it's not made of corn, it's made of black wheat, I guess. So let's talk about research activity now. In this first presentation, the slides are in French, so I apologize for this. So my lab is structured in this form since 6 years now. He gathered, in fact, 3 thematic laboratory, one of polymer and composites, one of mechanical engineering, and the last one of thermics and energetics. And we put all these things together to make a big lab of design of material. So the center of gravity is located in Lorient on this map here. When you find thermics, mechanics, and polymer and composites activities, we have a small team who is dealing with biophysics in Vannes. Some colleagues, we are working in a military school on mechanics in Guerre. A small team also on bioprocess in Pontivy, and a few colleagues are working on rheology in Brest. Brest is the biggest town in our area. So at this time, the lab gathers around 150 persons, 60 researchers and teachers, 28 engineers, technicians, and administratives and executives, and around 60 PhD students. Sorry. What I have to say about this is about engineers and technicians. We have only on these 28 5 people that are functionary paid by the government. All the others I paid on contract, on the project, and so on. So the lab is recognized by the French Ministry of Teaching. It is one of the 13, now there is 13 laboratories of research at the UBS. It is the largest one at the UBS, and the main tutel is the University de Bretagne Sud. What we are doing in this lab is to create materials, new materials, but we are not studying materials at the atomic scale. We are studying materials to do parts, to do smart structures in order to use it in the real life. That's the way that we are dealing with material at the lab. So we are dealing with several things here. We starting from resources, so we create, for example, composite material from bioresources, hemp fiber, flax fiber, and so on, bioresins, and so on. When we have done this, we are doing some formulation, elaboration to create new materials, new samples. And after, all what we do is to characterize this material in terms of mechanical properties, thermal properties, and so on, electrical, and so on. And by doing a transformation process, we have created some parts that can be used in the real life. So the main material that are involved in our studies is the composites, the polymers, and the metallic materials also. We are divided in 5 teams. So I will tell you what we are doing in each of these teams. The first one is polymer and composites team with three main activities, 3 main fields. The first one is, as I told you before, the creation of biopolymers and biocomposites with specific performance in order to do some structures. The second one is the nanocomposites polymer. So what we do here is to add some carbon nanotube, in polymer in order to create a polymer that is conductive of electricity, and then we can use it in sensors. You will have a large presentation of this team by Jean-François in the afternoon. And the last one is the rheology of polymer systems, associative polymer system. Once again, it consists in putting some loads, some small loads in polymers in order to improve the mechanical properties or several properties that we need. The second team is concerned thermal activities. So in this team, we are dealing with welding. This is a large activity in the lab. Welding, different types of welding, spot welding, flux welding, and laser welding, and so on, both in the experimental activity and in the modeling of this process. We are also dealing with the optimization of heating process, drying and heating process. For example, we are working a lot on vulcanization process in order to create some elastomers, for example. But we are also dealing with specific French problem. This is the optimization of oven to cook the bread. So what we are doing is to optimize the oven. And here you have 2 baguettes here. So we tested a lot of baguettes in order to determine what is the best conditions in order to have a good bread. And the last activity in this field is the use of the creation of new isolation material for construction. So, for example, here in this area, we are dealing with hemp concrete, so we create new concrete with bioresources in order to put in houses to make the isolation of the houses. So we are trying to find the best mechanical properties, the best thermal properties, and so on. Let's talk now about mechanics. So once again, in this team, we have three main fields of research. The first one is process of sheet metal forming process. The first one here. This is the field in which I am working in. So it's most of on metallic materials mostly. The second one deals with dynamic of materials, so it's high strain rate solicitation on metallic material, but also on polymers or composites, to determine the relation between forces and strain rate and so on, and deformation. And the last activity dealing with numerical method in coupling fluid and structures. So the flow of a fluid along a structure and to modelize the flow of the fluid along the structure. Another team of mechanics which is working mostly on civil engineering. So they are dealing with big materials, big structures. Sorry. So the difference between what we are doing is the other mechanical team is that we are dealing with kind of mechanical approach which are quite different. This one uses macro approaches, as in the other team we are mostly using phenomenological approaches. And the first axis corresponds to the rheology of heterogeneous media, so fluid or not really fluid, and we are dealing with the mechanical relation between shear stress and flow of the material. And the last one deal with some biotechnologies. So three main fields. We are working on waste materials. So traitement et valorisation des azotés mean nitrogen effluent. So we are dealing with methanization, for example, cleaning of agroalimentaire installations, and so on. And the last two axes are dealing with the link between material, a kind of material that we have created, and the way as it can be dangerous for humans. So that's the last two parts, and what we are studying in this is the link between what is dangerous and what can we do with polymer material, for example. Here we have the different degrees in which we are involved. The researchers of the lab are teaching or managing these degrees. So we already seen some in the previous presentation. So we have licenses bachelor, biology, civil engineering, energetics, mechanical engineering, polymer and composite, and eco-design. We found once again in master nearly the same things. So materials, mechanical engineering, energetics, and so on. And there are also three M2, so it's the highest degree before the PhD, in which we are going to find our students to make a PhD in the lab. So it's material, C-nano, so nano materials, and energetics. And these here, you have also several other degrees in which we are teaching. So this is GUT is technological for technological student. L-Pro is for a bachelor degree in which after you are going to work. So it's more applied than on the left side. Mechatronic is a degree of the engineering school, and Sigma is our doctoral school. So this is a picture of not the last, but before the last general assembly of the lab. So we are now 157. We had a large increase during the 4 last years. Some indicators of the lab. So this is the number of EC means teacher researcher, so we are nearly stable on this part. The second one is for engineers, technician, and administrative, so we are quite stable also. But we had a large increase of PhD students during the last 4 years. Mostly because we are we made some foreign students to come to study in our lab. So we have 27 and 61 people that can supervise thesis. That's what it means. 27 HDR over 61 teachers. This is the financial support of our PhD students. So some of them are supported. One thing is that we have to pay the students when they are in PhD thesis in France, so it's compulsory. We have some different kind of financial support that we can have here. Some of them are CIFRE, means that they are supported by an industry. DGR is military financial support. Établissement, it means that they are supported by the French government. Collectivities, it means that they are supported by the region, the town, and some collectivities in Brittany. And a large part concerns the foreign students, is the pink one here. So we have, with all these, around 60 PhD students at the moment in the lab. There is around 15 PhD defense per year. So this is the number of foreign students in the lab in last year. So most of the foreigners came from North Africa, Morocco, Algeria, and Tunisia. Why? Because they speak French, so it's more easy for us. But we have also several students coming from India and Indonesia, Germany, Portugal, and so on. For all these students, they can make the PhD in English, but it's good if they can learn French during their 3 years, but they can do everything in English if they want. So it's a good opportunity for students that are here if they want to come to make a PhD in our lab. So they don't need to learn French if they can speak English well, but they have to write the manuscript in English, so it's not so easy. This is for publication of the lab. So we increased a lot during the last 4 years. We were around 65 publications. This is international in very good journals. So 65 per year, and now we reach 90, 100 publications per year. So we have very good dynamic on this topic. We are invited in several conferences, and the other are conference and communication. So the average of publication of the one teacher researcher in the lab is 2.5 articles per year and per researcher. So it's a good rate. This is the financial budget of the lab. So it is a little bit decreasing, but it's around 2.5 million euros per year. It makes 50 million pesos, I think, around. So it's very large for a research lab, because we have many industrial collaboration with many partners. So we will see it a little bit after. So even if it decreases a little bit since the crisis in Europe, we have a kind of large resources in the lab. So it means the average gives around 40 kilo euros per researcher. So this is the industrial collaboration. So you can see that they are mostly localized in Brittany, but we have also in all the country many good collaboration, financial support for PhD students and so on. So this gives you the distribution of the companies that are working with us. So Morbihan, it's the place that we are living, near Lorient. So around 30%. After 20% in Brittany, and the rest in France, and some few abroad. So this is our main collaboration, international collaboration. when I put some countries in colors, it means that we have some recognized collaboration. Even can be financial support, for example, different kind of things, or collaboration, publication, and so on. It's not only a discussion between two researchers. So the main country is Algeria. So the most it is dark, and the most we have cooperation with this state. China, India, United States, Canada, and Australia that are the most powerful collaboration that we have. So this gives you just a resume of what I tell you today. So the research activity is the life cycle of structures from the material to engineering design. We are around what you have to memorize, 150 persons, between 80 and 100 international publication per year, 15 PhD defense per year, 4 patents. This is quite variable, but around 4 patents per year, 2.5 million euro budget without salaries, and 3 main topics. Even if we have 5 research groups, we have 3 main topics: polymer composites, mechanics, thermics. So this gathers what we are doing in each field. So this is the end of the presentation of the lab. Maybe if you have already some question about it, I can answer.
Did you have any question for this part of the talk? You can make a question. Anyone? Jim? Okay.
I wonder about the materials that you do in this lab. Are materials for the needs of the region, or you make the design? I don't know. I mean, I want to tell you that, for example, I listen that there are small factories near in the town or in the country. They ask you for materials, and then you synthesize and create, or they ask you for some studies of mechanical properties, or you design the materials?
Yes, it's a good question. I'm going to answer with an example. In the region of Lorient, there are many companies that are dealing with nautism. It was told before. So there are many small companies that are building boats for nautism, for sailing and so on. And most of these boats are made with traditional composite materials. So when the boat is going to be old, it's going to be a waste on the coast. So it's not very nice to see these boats at the end of their life. So what we are going to do in the lab is to create some new material, new composite material with bioresources. Like that, these boats could waste by themselves at the end of their life. So the problem is that how can you build a composite material with good mechanical properties, with good adhesion between fibers and matrix, so this is a research field because the company doesn't know how to do this. Okay. Another field is what Virginie presented before, is about compositic. We have a transfer structure near the lab in which we are dealing with composite material again, but instead of manufacture the composite material, most of the time it's made by the hand of the man. We are trying to use a robot to put the fibers and the resin at the same time. Like that, there is no human manipulation and there is no defect in the composite. So this is also a research field, and for the moment we are using only carbon fibers or glass fibers, but we are hoping to use also flax fiber or also. Okay? So this is in the composite field. We have also the same things with polymer materials, also the same thing with metallic materials. We are often asked for the automotive industry to define new process, to define new materials, to change something and so on. So we have a lot of work to do. For metallic material, I'm going to present it after, on the second part.
Okay, thank you.
¿Alguien más? Anyone? You?
Hi, I heard something about carbon nanotubes in the area of nanocomposites. I wonder if you do or if you are interested about theoretical research in this area, about, I don't know, modulate some carbon nanotubes or something like that. But I don't know if you are interested or if you do it.
What properties do you want to model? Is it mechanical, electrical, or?
No, about the molecular structure, the properties of the
threshold, for example, and so on. Maybe you can. Jean-François is the main researcher in this field. Maybe you.
I can present you in more detail this activity this afternoon.
Okay.
Because we are working, for example, with sensors. They have
Si ustedes tienen alguna pregunta en español, tenemos la ayuda de... ¿Está Miley todavía? Bueno, está Francisco, que nos puede ayudar para hacer la pregunta o respondernos, ya sea en francés o en inglés. Para si alguien tiene una pregunta, la podemos hacer. Está Alma también ahí atrás, con el inglés, por si alguien tiene alguna duda. Entonces nos pueden ayudar en esa traducción, tanto para la pregunta como para lo que ellos contesten, ¿verdad? ¿Ok? Ok.
Organization. I think I don't need the microphone to ask the question. Just 150 persons adscripted working in this laboratory. They are concentrated in the same area, or they are for different campuses.
As I mentioned at the beginning, in fact, we have 80% of the 150 that are localized in Lorient, and the rest are localized in several campuses: Brest, Pontivy, Guer, and Vannes. So these 20% are small teams of 4 or 5 people in each, in different campuses.
So the first question. The other question is the 90 persons, how do they organize? It's the only one administrative unit, let's say, one laboratory, you have one area, or you have a few sub-laboratories and so on, sub-groups, and how is it organized? Because you have quite different topics to investigate.
In fact, we are divided in 5 groups, 5 teams that I presented today before, and we have so an organization. We have one director with vice director and 5 research team leader, and that's the head of the lab. And after, in each team is independent in terms of research activities, financial activities, financial budget, and what else? And personal. Educational is not linked directly to the lab, so it's something else.
Do you have some responsibilities, educational responsibilities in each classes or lectures?
Yes, we do.
So the question may be not directly related to this lab, but the organization. As I understood, you have a quite flexible educational program. And you have a lot of 2 years programs, 2 and +1, 2 +2, and master degrees and so on and so on, and also interdisciplinary, different specialization. How many administrators do you have to manage all these administrative links?
That's a really good question. In fact, it's a real problem. It's a real problem because we don't have many administrative people to manage these degrees, and most of the time it's the researcher teachers that are doing this job. So when we are doing this, planification of the time, of the courses, of the lessons, and so on. This is made by the researcher teacher. So it's time-consuming, and when you are doing this, you're not doing research. So it's a real problem for the lab. We have too many degrees to teach.
Specialist orientation, career.
Mostly, there are 3 kinds of specialties like mechanics, energetics, and polymers and composites, master degrees. So this fits quite well the 3 teams in research. Then we have additional diploma and professional diplomas.
Yes, so this kind of, that's I refer to. The question is also, it's a network, and I had an impression that anytime a student wants to say, I am ready, you have a title of this or this level, and you can go out of...
there are some transdisciplinary teachings. Like mechanics, for example. Mechanics are polymers and composites, energetics also. And energetics courses are also in polymers and composites. There are some cross courses.
But most of the time, it's a kind of vertical formation. A student that chooses mechanics is going to stay in mechanics until the end and is going to do a PhD in mechanics. So it's more or less linear.
I would like to ask you more in details a little bit later, because it's quite interesting how do you bank the students to the final title, I would say, and it's a little bit delicate. How do you oblige them to take these courses from the initial to the final, or they choose in any way on this?
It's not compulsory, but most of the students they follow the spring time. For example, otherwise it's too complicated to manage the timetables and everything. So in the first years of bachelor, there's a larger choice, and then the choice is decreasing as you are doing
Okay, thank you. Let's continue, no? Because we don't have more time. A lot of time.
Okay.
Okay, thank you.
No, I keep this microphone.
Yes.
So I am going to present some research activities. In fact, most of my research activities for the moment deal with sheet metal forming of metallic materials. What I'm going to present here is some recent work because I had a PhD student that finished his PhD in June, so I will present his results today. So this presentation deals with warm forming of aluminium alloys. I will tell you why we are doing warm forming, and with this particular effect, which is called Portevin-Le Chatelier effect. I will explain you what is this effect, and how can we characterize in a more to improve the characterization of this effect using monotonous shear tests, cyclic shear tests, and I will conclude on this work. So, during the last, I told you in the title that I'm going to deal with warm forming of aluminium alloys, because during the last 10 years, the increase of aluminium alloys in the automotive industry increased by 80% in the last 10 years. So, this is in the topic of lightening of vehicles that everybody is going to have in the 10 next year. But there are several problems that still remains, that the price of aluminium alloys is more expensive than steels. The formability of this material is lower, and there is a high spring back of this material. So you have on this picture here, this is a car, and all these parts are made here by sheet metal forming. This means that we take a sheet, which is initially flat, and with some tools, we are forming the sheet in order to obtain the final form. This is called sheet metal forming or deep drawing. This is the process that allows to do this. So it is a very old process. It's known still. People are wearing armors, for example. This was already done by this at this time. But before, it was made with steels. So we have a very large knowledge of sheet metal forming with steels. And now, in order to improve the weight of the cars, the car manufacturer are changing steels to aluminium alloys. So there are two current trends in the use of aluminium alloys. The first one is the replacing costing alloys, typically 6,000 aluminium alloys that are used for the moment, which are very expensive, by cheaper ones. This is our main idea, is to use 5,000 aluminium alloys that are much cheaper than the 6,000. And in order to be able to do the parts, you have to warm form these aluminium alloys nearly to 200, 300 degrees. If not, it's not possible. You have breakage of the sheet when you are doing sheet metal forming. The problem is that when you use 5,000 alloys instead of 6,000 alloys, you have a special defect that appears on the sheet that you can observe here. And this is a front panel of an automotive. And if you have a closer look, if you have a zoom on this part here, you have some straight lines here. And this is, we can't use this for cars, because when you are putting the painting after on the car, it makes several defects and it's not nice. So people won't buy some car with this. So we have to find a solution to avoid this effect in order to use this material, which is quite cheap, instead of costing aluminium alloys. So this effect is called Poitevin-Le Chatelier effect, and it appears in kind of conditions between temperature and strain rate, and in the region in between these two lines here, these effects appear. If you can be here or here, you won't have the effect, so it can be done. So what is this effect? It describes a jerky flow. I will show you some curve with a jerky flow that some material exhibit when they undergo plastic deformation. So what we call plastic deformation is to deform a sheet from an initial flat form to a deformed one, under particular condition that I showed you before, and which is characterized by an inhomogeneous deformation. I will show you some samples after that present this kind of thing. So it is an defect that is known since a long time, and been discovered by two French guys, which is called Poitevin and Le Chatelier, in the years 1920, around this. It is present in several materials, aluminium alloys particularly, and particularly aluminium magnesium alloys, but several ones, copper alloys, iron alloys, and so on. It is mostly observed on flat samples, not on sheets, and has been highly studied in the literature in the last 20 years at least. So if you do, this is a classical mechanical curve. What we do here is to plot the stress against the strain. So this is the more classical mechanical characterization. You take a sample and you pull it in one direction, and what you measure is the evolution of the force as a function of the deformation. Okay, this is typical mechanical characterization. Usually, when you do this on a normal material, you have a smooth curve that goes from this part here. So you start from 0 here, you have an elastic deformation, and then after you have a plastic deformation. The transition between the two, it means that if you are here and if you remove the load, you go back to this position. If here you remove the load, you go back to this position. So you have an irreversible strain when you are reaching this part. So instead of having a smooth curve, you have here a messy curve, a tricky curve with several oscillations here. And this is produced by this typical effect. So, which is due to, in fact, a competition between diffusing solutes that are present is, for example, in aluminum magnesium alloys, so the solutes are the magnesium atoms, and the pinning dislocation, and the dislocation breaking free of the stoppage. So each time, when you are deform plastically here a material, you have what we call a dislocation. This is the defect in the metallic material. And when this defect reaches solute atoms, so magnesium atoms, they are stopped here. And then you have to increase the stress in order that the dislocation here moves again. That's why here, it doesn't work anymore. That's why here we have some serrated curves. You can see this, and this is what I told you before. So this is a tensile test here. This is a tensile sample. You have here a band that appears at the bottom of the sample, and then this propagates in the sample, like vertically to the top. So when the band propagates, it creates several bands that remain on the sample and that are not nice at the end. So this effect depends on many things. The strain, you can see here on this figure, for example, that the effect will start nearly here. It depends on the strain rate. So we have here 3 different strain rates. The highest one here, this is the lowest one, and this is an intermediate. So the variations are very different depending on the strain rate. They are depending also on the temperature. So if you reach a sufficiently high temperature, we can see that we will see later that we can suppress this effect. And it depends on magnesium alloys and magnesium aluminum alloys on the magnesium constants, but we didn't study this effect. We always used the same alloys with the same percentage. So the different types of bond that can be observed, you can have sometimes one unique bond crossing the sample, as in the previous picture. You can have a set of several bonds crossing the sample, and that generates a very serrated curve. And you can have random bands that are crossing the sample in every direction that create very large here serration on the curves. So if we plot here the evolution of the critical deformation in order to observe the Porto-Valois-Chatelier effect as a function of the strain rate here, we have a tricky curve here which depends on the temperature and depends on several parameters. And what we can see here is that all these curves have been observed in tension, and in tension it is impossible to reach strains that are higher than 1 or 15% of plastic strain. So what appears here up this curve for larger deformation that are involved in the sheet metal forming processes. So what we think at the beginning is that tensile test is not sufficient to model the Porto-Valois-Chatelier effect for processes such as sheet metal forming. So we investigate, we try to find another type of test where the strains are larger than in tension. So that's why I use other type of test here. So as a conclusion of this third part, the Porto-Valo-Chatelier effect is a complex material effect that depends on strain rate, temperature, and alloying elements. It causes a negative strain rate sensitivity, we will see it after, and it causes rough surfaces during deformation that render them useless for automotive applications. So how can we improve the knowledge on this effect? The first thing is the occurrence on PLC effect on other strain paths, the investigation of larger strains, cyclic and pre-strain effect, and the investigation, of course, on temperature and strain rate effect. That's why we use a test that we are used to in the lab, is the simple shear test. So what we did is to use this kind of sample. So we cut some rectangular samples on a sheet, on a metallic sheet. And then by this machine, this kind of machine, we are going to do a shear test on the central zone here. So we fix the sample like that, and we move one grip to the other. So we create a shear test in the sample. And we put all this in a furnace. In order to measure the strain, we are using a video correlation technique. So we put a painting on the sample, and we measure by two cameras that are located here. Maybe you can see them. Two cameras here that measure the strain of the sample on the whole gauge length. So this is the material that we choose. It is a classical material that is used for inner body panel in the automotive industry. The sheet is 1 millimeter thick. And this is what we obtain on a shear test. So this is the curve representing here the stress, the shear stress, as a function of the shear strain. The first thing that we can observe here is that there are some serration of the curve. This is the first time that this has been observed on other type of solicitation than tensile test. The second one is that we can reach really large strains up to 0.8. As I mentioned earlier, in tension you can reach higher than 0.15. And we have here an effect that depends on the strain weight. We have tested here 3 strain weight, V1, V10, and V100. Each time the speed is 10 times higher than the previous one. And what you see here is that the lowest speed is the highest curve. So this is the more, how can I say, rough, tough material, sorry. Not rough, but tough material is the one which is obtained with the lowest strain weight. This is not a normal effect in metallic material. Usually when you increase the strain rate, the stress is higher. So what we observe here is typically a negative strain rate sensitivity, which is, that is plotted here on this table with this value of the different stresses that have been reached. What we observe also is that the acceleration of the first speed is higher than the others. This is called the first part here, the first non-linearities in the material is called the Pierre-Yves plateau. And you can see on this figure how it goes here. So this is the zoom of this part here. And I have here a picture of the zone where we measure the shear strain. And what you observe here is 2 bands that are crossing the sample in the direction perpendicular to the shear stress. If we go now a little bit farther, this is another speed, sorry. You have here a band that is crossing the sample on the direction perpendicular, but the unique one in this case. So the form of the band that is generated depends on the strain rate. So after we characterize several things, so typically the width of the band, depending on the strain rate. So what we observe here here we made several sections here, and we plot these different sections, and we measure the strain rate in this region. And what we observe is that this is the average imposed strain rate. In the band, the strain rate can reach 5 times what the speed that is imposed in the sample. So the bandwidth evolved with the strain rate. It increased from 0.7 with to 1.4 millimeter, and increase also with the velocity. After we measured here the stress jump for each curve, and what we observe is that the distribution of the stress jump is not the same depending on the strain rate. For the lowest one, for the red curve, we have here a Gaussian distribution here. As for the two other strain rate, we have a decreasing evolution of this stress jump. So this is typical to what have been previously observed on tensile tests. The V1 correspond to TB bands, so I didn't explain this before, but correspond to TB bands, and this one, the other one, to TA bands. What we observe also is that the orientation of PLC band varies with the strain. At the beginning, the bands are nearly vertical, so parallel to the shear direction, which is vertical in this direction. But when you increase the value of the strain, when you are reaching larger strains, the band started to rotate to a direction that goes from both corners of the sample, from the top to the bottom here. So there is a rotation of the band as the strain increases. When we started, all was done before was made at room temperature, but when we started to investigate the temperature, we get very messy results. But we can explain it. 5 minutes? But we can explain it. What you observe here is that at 25 degrees you have the red curve, so the one I presented before. But at 100 degrees you have the green one. It means that the stress is higher until a point where serration starts, and then after it crosses the first one. This is not a typical effect in metallic material. Usually, when you increase the temperature, the stress decreases. This is what we observe for the two other temperatures. For 100 degrees and 200 degrees, the stress decreases highly. So, in this region, we have a complex material behavior induced by the PLC effect. The PLC effect starts here. It means that there is a critical strain for PLC occurrence at 100 degrees, and this could not be observed in tension, because if you see, we have observed a starting of the PLC effect for a strain of 0.3, 0.4 deformation, and that couldn't be observed in tension. So that's enlarge the perspective of what we can see with this test. And we have the impression on this curve that the PLC effect disappears at around 150 degrees. But this is only an impression, because this is not true, in fact. At 150 degrees, we have, depending on the strain rate, we have different kind of curves that are crossing together. And if we have a closer look, here we have an inverted effect. The stress increases at the beginning, and the stress decreases at the rupture, at the fracture. And sometimes we don't have PLC effect. You see, we have an homogeneous strain field, and sometimes we observe clearly some bands, even if the serrations are really small. So this test shows something that have never been seen before. At 150 degrees, you can have also PLC effect, depending if you are able to investigate large deformation. This was not obtained before, so we are happy with this result. So to end my presentation, this is a more complex study on cyclic tests. So what we are doing, this is an advantage of the shear test, is that we can do shear test in this direction and we can do shear test in the other one. So we can do cyclic. In tension, you cannot do this because if you are doing with flat sample, you cannot do compression on flat sample. It's going to be what we call bending of the sample. And we observe here different, several kinds of complex evolution. For example, when the PLC effect is present, we have an increase of the stress when we reverse the solicitation. This is not a normal effect on neither. But when we are reaching 100 degrees, we have a competition between two effects, what we call Bochinger effect and what we call PLC effect, which means that the PLC effect will start for a critical strain that decrease with the pre-strain, the value of the pre-strain of the first pass. And we observe here that it's not really a critical stress, but more sure a critical stress that will start the PLC effect in the second pass. So, is it a critical one? So this is all the results that we have obtained in this study. I already comment all of this, so this is the end of my presentation. I think it's within the time. Thank you very much.
Thank you. We have time to any questions? Okay. No? Okay. Sorry.
I saw this strain-stress relation curve. It reminds me the behavior of rubber materials or like sheets also. This kind of also increase of stress, very at the initial of the strain, and then they even the lower, and then they follow this kind of. Do you have this experience of working with these materials or characterization of these materials, the sheets of rubber, for example?
I already did this kind of study several years ago. In fact, when you have an elastomeric materials, you have only, most of the time, elastic deformation. This is different of what we have observed here. Because in a rubber, you will have a curve which does like this, and when you unload the stress, you will go back to the initial deformation mostly. In this kind of metallic material, what you see is that when you reach here a high level of strain, when you're unloading, you're staying at the same point. So, no, you have a very large, you can say that we have a very large hysteresis, but we don't have an unloading. No, you can't. You can only return in this region here. If we make a zoom here and we unload, we can return to the initial position. This classic as distinction in metallic material between elastic deformation and plastic deformation.
But we have some machinery or like a kind of experimental devices to characterize this kind of problem?
Yeah, we have. Yeah. Oh, good.
Yeah, that is the reason the next part of the program, to do many things. Okay. Any questions?